Hello again, and welcome to another lesson in the Designing VMware Infrastructure video training series. In this lesson, we're going to be talking about creating the logical storage design. In this lesson, we're first going to start out by examining the logical storage design. What's included in the logical storage design? And what do we have to specify when we create the logical storage design? From there, we'll move into a discussion of how we go about calculating the specifications that are included in the logical storage design. What numbers are involved, what values do we have to obtain, and how do we go about manipulating those values to get the specifications we're going to include. And finally, we'll wrap up this lesson with an examination or an exploration of the related areas in the design. In other words, what areas are affected by the logical storage design and what areas affect the logical storage design. This is part of our ongoing effort to continue to maintain a holistic view of the design so that we can account for and address design impacts as we proceed through the design process. First, let's talk about what needs to be included in the logical storage design. As I've shared with you in other lessons in this course when we've been discussing other types of logical designs, such as the logical compute design or the logical network design, the logical storage design is going to be a high-level design. We're not going to get deep into the technical details of how we're going to accomplish this particular storage platform or storage solution. We're not going to specify products. We're not going to specify particular solutions, but instead we're going to specify what the storage has to provide. And what we're going to do is we're going to do that by specifying basically maximum values or requirements that the storage has to be able to supply to the environment. And we do that through specifying values like the total number of IOPS that the storage design has to accommodate. In this case, IOP is an I/O operation per second. It's a measure of a transaction occurring on the array. We're going to also specify a total number of throughput in megabits per second or megabytes per second or even gigabytes per second. We're going to specify a total storage capacity, typically in terabytes, although in small environments it might be specified in gigabytes. We're going to specify expandability. How much room do we have to grow the storage environment, both from a storage capacity perspective, such as I can add additional X number of terabytes, but also from a throughput perspective, I can add more ports to carry more traffic. I can add more drives to add more IOPS support, those kinds of things. We're going to specify RPO, RTO, and talk about how we're going to satisfy the RPO, RTO in the logical storage design. And finally, we're going to provide in the logical storage design some broad allocation guidelines. In other words, how are we going to provide this storage out to the VMware environment? As you've just seen, there's a fair amount of information that's going to be included in logical storage design, so you might be wondering, where am I going to get all this data? Where am I going to get these numbers that I can include? And then how do I take the numbers that I get and turn them into what needs to be included in the logical storage design? Well, recall in another lesson in this course as we were discussing the process of defining the requirements that you really need to do an assessment of the current environment. If the organization for which you're doing the design, whether it be your own organization or a customer, is going to be rolling existing workloads into this new environment, we really need to assess those existing workloads. If they're going to be rolling brand new workloads and turning them up into this environment, so that we don't have anything to assess, then we need to have some sort of information about what those workloads are going to generate. So in an existing environment, we can use tools like Capacity Planner, other third-party assessment tools, or even OS-specific tools like Performance Monitor or others that would tell us what sort of activity is going on. For example, you can use Capacity Planner to get the total number of IOPS that are out for all the systems that are assessed, or you could use something like Performance Monitor on Windows to determine how many IOPS a particular Windows instance is generating. You also need to have an idea of the I/O size. That will tell you a couple things. One, larger I/O sizes generally have an adverse impact on IOPS, meaning that the larger the I/O size, the fewer number of IOPS a drive can generate. And also the I/O size multiplied by the IOPS is going to give you your total throughput. So a high number of IOPS might be a small I/O size and therefore not a great deal of throughput, but those are addressed in different ways. Whereas a larger I/O size might be a lower number of IOPS, but would be a higher amount of throughput. And so each of these different dimensions we have to address in the logical storage design. Total storage capacity is probably the easiest one. It's going to be the sum of all the current storage usage plus your projected growth. So if the functional requirements say that you need 20% growth or 30% growth or 40% growth, whatever the number is, you have to include that in your total storage capacity. By the way, you also do need to include that in IOPS and other dimensions of storage as well. Your RPO and RTO are going to be generated straight from your requirements analysis. So that's going to be based off the information that you gathered from the business, from the key stakeholders in terms of what they provided you and what was signed off by the project team when you did the requirements analysis and define the 4 design factors: requirements, risks, assumptions, and constraints. Finally, the broad allocation guidelines, as I mentioned, are going to give some rough ideas of how you're going to go about taking that storage and presenting it to the VMware environment. The logical storage design will say, I'm going to present a total of 25,000 IOPS, and I'm going to present a total of 3 terabytes of storage. But how are we going to carve those IOPS and that capacity up and present it to the VMware environment? That's what we're talking about when we talk about the broad allocation guidelines. And that in particular deserves a little more attention to detail. So I'd like to discuss how we arrive at the broad allocation guidelines in a bit more detail. So how do we arrive at these broad allocation guidelines? What we're really talking about here are data stores. We're talking about how we take a logical storage design, which is a logical pool of capacity and IOPS and throughput, and how do we carve that up into logical constructs or logical containers or logical buckets, and then present those containers out to the VMware environment. How do we go about actually coming down to determining what the size of those buckets are? Do we just kind of offhand say, hey, I'm going to go with a 2 terabyte data store and then hope that it works? Or is there a process that we can follow that would help us arrive at some sort of optimal value? There is actually a process and a set of calculations you can go through. Now, we're not going to talk as much about IOPS here because we generally handle IOPS in the physical design, and many arrays decouple capacity from IOPS through a variety of storage pooling mechanisms or auto tiering mechanisms, and we'll talk more about that when we get into the physical design specifications portion of the course. But we are going to be talking about size in gigabytes or terabytes and how that is a function of your average VM size, the number of VMs, and the RTO, RPO for your environment. And you're going to analyze all these factors together to arrive at an optimal data store size that meets the functional requirements and satisfies the other design factors. So what I'd like to do now is actually take a look at how we calculate these values, how we arrive at an optimal data store size using some of these values that we've gathered and collected. So what I'd like to do now is take a look at some of the calculations that we have to go through if we're going to calculate what our allocation guidelines should look like, how we're going to carve up this logical pool of capacity into data stores to be presented to the VMware environment. What are the numbers that we need to use, and how do we use these numbers to come to some sort of data store sizing mechanism? So what we're going to do first is there's 2 basic calculations that we need to look at here. The first calculation is around how the RPO RTO plays in. So I'm just going to divide this slide in half here, and over here we're going to, on the left hand side, we're going to calculate or we're going to look at how RPO RTO comes into play in the mix. So on this side we're going to look at RPO, and on this side we're going to run a calculation based on VM size. So over here under RPO, the key here is knowing that we have to satisfy the RPO for a given data store, and the RPO being how much data we can afford to lose. And so we have to look at both RPO and actually we have to look at RTO here as well, which is our recovery time objective, and actually RTO is probably a more accurate indicator here. But we have to go work through some assumptions here. So let's first start out with saying that we're going to look at a backup solution, and let's say that this backup solution is capable of backing up some amount of data. So let's say that this backup solution is an LTO5 tape drive. Now we know based on the specifications for LTO5 that there's a certain amount of data that it can read and write, a maximum amount that it is able to restore within a given time period. For example, on an LTO tape drive, the theoretical maximum for restoring data is 140 megabytes per second. That translates into a total when it comes to over time, because megabytes per second doesn't really help us that much. That translates into a total of just about 500 gigabytes in an hour. And with that in mind, then we can take a look and see if I've got a backup mechanism which is capable of restoring data or backing up data at 500 gigabytes per hour, theoretical maximum of 500 gigabytes per hour, and I've got an RTO of 2 hours, then I need to be able to restore an entire data store within 2 hours in order to be able to be guaranteed that I can meet my RTO. So if I'm restoring data at 500 gigabytes an hour and I have a 2-hour RTO, then that means that my maximum data store size is going to be 1 terabyte. That's 500 gigabytes an hour times 2 hours, for a total of 1 terabyte. That guarantees that if I size my data stores no larger than 1 terabyte, and I have an outage of some sort where I have to restore an entire data store, I can be assured that I can restore that entire data store off this particular backup solution within the given RTO and be able to meet the service level agreement with regards to availability that I've established with the business. So looking at data store sizing, one calculation to look at, and one way of looking at this is through looking at your RPO RTO. The other way of looking at this is through the VM size. All right. So let's, again, we might have some data, some raw data here, but just for the purposes of looking as an example, let's say that we're going to say that our VMs are going to be 50 gigabytes in size. So how many VMs can I fit into a 1 terabyte data store? If I carry this data across and I say, okay, I've got the 2-hour RTO, which means I'm going to propose a 1 terabyte data store, and my VMs are 50 gigabytes, then how many VMs does that translate into? Well, if we start doing the math, okay, then 10 of these VMs would be 500 gigabytes, right? So 20 of these VMs now becomes 1 terabyte, which means I can get 20 VMs in a given data store if I size the data store at 1 terabyte. Now, that doesn't account for all the other pieces that need to go in here, such as VM swap or snapshots or data store slack space, an extra certain percentage. So you might actually even be looking at only, let's say, 18 VMs, which would give us a total of 900 gigabytes of used space out of a 1 terabyte data store. That's a 90% utilization. All right. If you're still concerned about 90% utilization because we haven't specified what the memory is on these VMs and how much space is going to be required, you might even need to drop that down. Then if we go from 18 VMs, we'll drop that down to 16 VMs, which then drops us to a total of 800 gigabytes, which is 80% utilization, which is a more common figure saying I'm going to maximize my data stores by making sure that there are no more than 80% utilized. So these two figures, then what you can do once you've done that calculation is you can say, okay, if I have a certain number of VMs, let's say I have 200 VMs, right, then, and I'm going to get 16 VMs per data store, then I'm going to have to go in and create a certain number of data stores in order to have enough data stores, to have enough VMs with enough space to do what I need to do. This kind of gives you an idea of how you can use the numbers that you've gathered from the requirements analysis, like the RPO, RTO, and the backup solution, either existing or proposed, and what it's capable of doing, along with information on VMs that are going to be imported into this environment if they are bringing in new workloads, or existing workloads rather, as well as assumptions or requirements on what new workloads are going to look like. You can then use these calculations to determine what would be an optimal data store size that still allows you to meet the requirements, and this then directly feeds into your broad allocation guidelines and how you break out the pool of storage in the logical design into data stores. Now that we've had a look at how we go about calculating the values and how we go about analyzing these different numbers and capacities together to determine how we specify the logical storage design, how we arrive at our allocation guidelines, i.e. our data store sizes, I'd like to wrap up this lesson with an exploration of the related areas and the relationships between the logical storage design and the components of the logical storage design and other areas of the vSphere design. Now, although we focus in these areas on looking at the impact that logical storage design and its components have on other areas, I want to reinforce the fact that these relationships are actually two-way relationships. So let's delve in for a moment. Look at the IOPS node here. Note that the IOPS node I have broken down. It says that it affects the type of array, it affects the number and types of drives, it affects your financial constraints, and it affects your operational processes. Even though we're kind of approaching this from one perspective, that is the perspective of the logical storage design and the IOPS, it's also important to understand that this is a two-way relationship, that the type of array will affect the number of IOPS that you can deliver. The number and types of drives that you put in is going to affect the number of IOPS you can deliver. Your financial constraints are going to affect the previous two options, which in turn will affect the number of IOPS that you can deliver. So although we look at this mind map from one direction or one perspective in terms of how the logical storage design affects other things, it is important to understand that the reality is that other things are also going to affect the logical storage design. These relationships are two-way relationships. Now, that may not be terribly important right now, but as we move into other lessons in this course and we start talking about mapping the logical design onto a physical design, in other words, when we take this logical storage design that we've defined and we then begin to select actual products and actual solutions, and we begin to map the logical design onto those actual products. So we say we're going to use a specific type of array and a specific configuration of array and a specific number of drives and specific types of drives and a specific configuration. Those decisions, as we map the logical design onto it, are going to affect the logical design. They're going to basically have a back pressure to say, well, I didn't put enough drives in, so now I can't meet the number of IOPS here, and so we're going to have to revisit our functional requirements, our risk constraints again, as we begin to take the logical design and map it onto physical solutions. And at that point, we might want to revisit these mind maps that we're sharing here from an opposite direction, taking one of these end nodes, like number of types of drives, and what is that going to affect? The nice thing about using a mind map is that you can do that pretty easily just by rearranging things. And it does give you a nice graphical view of how things are related to each other. So you can go as much detail as you need or want when it comes to exploring these relationships. As you become more and more accustomed to the relationships and the dependencies in a design, you might not find that your exploration, your related areas, your mapping needs to be as complex. But if you're new to the environment and you really want to make sure you haven't missed anything, you might want to make these more complex and go into as much detail as possible to ensure you haven't overlooked anything. As we now wind down this section on creating the logical storage design, let's review what we covered in this lesson. We started out with an examination of a logical storage design. What's in a logical storage design and what components are included in the logical storage design? From there, we moved into a discussion of how we go about calculating the specifications in the logical storage design. We take the values that are included and how do we manipulate those values and explore relationships between those values to arrive at the numbers that we need. In particular, I shared with you how we go about using values like VM size, number of VMs, and RPO, RTO to arrive at some suggested data store size guidelines. And finally, we wrapped up this lesson with an exploration of the related areas as we used a mind map once again, as we've done in other lessons in this course, to explore how decisions in the logical storage design can affect other areas of the design and how other areas of the design can affect the logical storage design and our ability to meet the requirements and other design factors that we've specified. That's it for this lesson. Thanks for watching, and we'll see you again soon.